So in this case, what we have is 3-point charge, and then let me call this charge Q1, and this
Uh-huh.
charge Q2, right?
Yep.
And this is charge Q3,
Yep.
right? So this V1 means potential at P because of Q1 would be V1 equals to formula, right? K Q1 divided by that distance R1,
The distance. Yep.
right? This is basically the
Mhm.
Pythagorean here, right?
Yep.
Okay. And then,
And
and because of Q2, there will be also V2.
mhm.
Because of Q3, you again do that Pythagorean, and then there will be V3, right? The same similar
Yeah.
formula. In this case, the distance is R3, R2. And then you can see V1 is negative, V2 is positive, and V3 is positive, right? Because the
Positive.
path is opposite.
Mm-hmm.
So the result will be like a minus, plus, and plus. So you add them together. So the value of V1 here, the value of V2 here, and value of V3 here. When you add them together, you get the total V.
So for the V3, are
Mhm.
we using the oh yeah,
Yeah.
the
Okay.
positive 4 and
Yeah.
the Q1?
Yeah.
Okay, I got it.
Q2 is
But
positive, Q3 is positive 6 microcoulomb. Yes.
mhm. And for the V2, or the distance is 0.02 or the slope?
0.02. There is no slope. There is only hypotenuse, for example, the Pythagoreans.
But from Q1 to P, it has a slope.
Not a slope, dude. That's called Pythagorean.
Okay,
Slope,
Pythagorean.
slope is angle.
Okay.
Got it?
Mm-hmm.
Okay. I know you what you mean. It's a slanted line, right? That's what you mean.
Yeah.
Okay, good. So that's how you do it. If you add them up, the answer should come out to be B, not A. Okay.
Okay. Oh. Mm-hmm. All
Okay.
right.
Mhm.
Appreciate you. And one more, I just don't know how to draw the electric field line.
But before we go
That's the
there,
mo
how did you do number two? And then what did you get for
I
this?
got E
Okay, makes
for
sense.
the number two. I
Okay.
just use because it has two charges.
Mm-hmm.
One is from the positive 2 microcoulomb, and one is from the positive 4 microcoulomb. And from the positive 4 to the point P, it has a Pythagorean. That's what, how do you call that, right?
So this one is number two is easier than number one then.
Mm-hmm. Yeah, because it only has like 2 points. It
Yeah,
doesn't have 3 points.
very good, very good. All right. Let me pause and then I'm gonna draw the electric field, okay?
Okay.
We okay, we kind of got that by uh let's say first we put the positive plate here,
Mm-hmm.
right? That's like a 10 volt up, and then there is a negative plate,
Yeah.
and then that's like a 10 volt down, meaning that this is 0 volt, that's 10 volt, right?
Mm-hmm.
So what you did was like let's say just for the case sake of argument, you found the points that are about 2 volt, right?
Mm-hmm.
And then 6 volt as an example, or the other way around. You found, I mean, as you go up, the value goes up.
Yep.
So you found the equipotential lines that have, let's say this is +2, this is +6, this is +8, something like that, right?
Mm-hmm.
So that's a series of line that you have, and then you draw something called equipotential line. In this case, you were drawing this, and then you can basically connect the dot, and that shows that these surfaces have the same potential, right?
Yep.
That's called equipotential line. And
Okay.
because of that, there is a color. Okay, well, because of that, we have the potential, and we saw that the electric field is basically the rate of change of, so the formula was E equals to negative delta V over delta X kind of thing, right?
Mm-hmm.
Where it is like a gradient. So as you go from this distance to this distance, that is my delta X. And then it went from +8 to +6. So if you were to now draw another graph, let me draw I can't change the color right now because it's not allowing me to. Okay, all right. It's not showing that. So if I were to plot delta x here and delta v here,
Mm-hmm.
that's the change, right?
Yep.
So we're literally looking at this rate of, like this is the rise over run negative, right?
Mm-hmm.
So from point, this is plus 8 volt, this is plus 6 volt. So you can see there is a drop of 2 volt, right?
Mm-hmm.
For the distance of, let's say, 2 centimeter. So the electric field E can be calculated, right?
Yep.
Or, the magnitude, for example, over here would be 2 volt change per 2 centimeter, right?
Yep.
The 2 centimeter is 2 volt divided by 0.02 meter, right? And
Mm-hmm.
that's like 100 volt per meter, right?
Yeah.
Now the question which I'm trying to like challenge you guys is to come up with a way to symbolize that, right? How big is the line gonna be? Because we know that electric field is gonna go from positive to negative, and I could draw that big line, or I could draw a small tiny line like that, right?
Mm-hmm.
So how do you decide? How do you normalize drawing, this line versus that big line, Because electric field is going definitely from positive to negative. But the question is for every electric field sorry, every electric potential line, you need to draw an electric field. How long, how big that should be? That's all. That's the question. Okay, so your value, for example, is if the electric field is 100 volt per meter, and if you decided to draw this line, which is could be 2 centimeter long, could be 1 centimeter long, could be half centimeter long, what is the scale that you need to write? In your map, they basically, if you look into the Google map, they show a map that says 20 mile is this big, you know
Mm-hmm.
right? So the question I'm not answering and you are thinking about is how do you come up with that scale? What is the scale that you are drawing on? So I hope that did not answer your question, but
Yeah,
still,
that did answer my question. So the overall things we need to answer is what is the scales between the positive charge to the negative charge and between the two electric
yep,
field line, right?
yep.
Okay, I got it.
I think we are on the same page now. So similar thing for the other one. You have the positive plate, you have the negative plate, and then you saw the potential was kind of doing this funny thing, right?
Mm-hmm.
That's like electric potential. If this is 0 volt, if this is 10 volt, as an example, right? So it's something like, so this area, I'm sorry, what? Not, I'm not going to talking about area. So in this case, let's say if this is 1 volt, this could be, I don't know, 3 volt, could be 5 volt, could be 7 volt, could be 9 volt, like something like that. And then you pound the electric potential line by doing the lab. And then, the electric field we know over here is going to be like this, right? And then it's going to be going like this because electric field is perpendicular to the potential, right?
Yeah.
So if you have this, theoretically we know, but practically you are to draw the electric field line here similarly, right?
Mm-hmm.
Now the question is again, same thing. How big the electric field line that you're drawing, you know? Right? So the answer is staring at you, it's that it's going to be like this, right? It's going to be perpendicular to the electric potential. Theoretically, it's that, right?
Yep.
But the question is how big of the scale that you are drawing at, So if you have a positive here, if you have a negative here, we all know that its electric field is going to be from positive to negative. But the question is how big the arrow that we are drawing. Does that make sense?
Yep. That all stuff making sense.
Very cool, very cool. All right. So thank you for asking this actually, because I think some other people might also be confused about this one, and answering this help provide.
Yeah, because our whole group doesn't understand those either. So I'll just share this with my whole group.
Yes, please do.
Hmm. And also, I have one more questions.
Yeah.
I have one more question. So if we have two charges, like one is -2 microcoulomb and
Uh-huh.
one is positive 2 microcoulomb, how do we draw how do we draw the electric field line just based on this two charge?
So what you are saying is that you have, let's say, uh, line. Okay. So there is a charge. Oops. Yes. Cancel. So there is a positive charge and there is a negative charge. Is that what you're saying?
Uh-huh.
And then they are separated by some distance. Is that right?
Yeah, they're separate by some distance.
Uh-huh.
Then
That
how do we know how do we calculate or I know the calculation, but I just don't know how do we draw the electric field line.
So the way it works is, let's say practically you would do the same thing, If you have a positive charge, you have a negative charge, you basically go around, like putting the point and then
Uh-huh.
find the lines that have the same potential. That's what we did in the lab, Find
Okay.
points that are the same potential and then you connect them, So unfortunately, I can't change the color right now, but and then you do that to find that it is equipotential line. And theoretically, as you saw, the electric field is gradient of the change of potential. So you basically draw a line that's going to be perpendicular to the electric potential. So as you go, over here, it's going to be like that. So electric field lines will come out perpendicular like that, right?
Mm-hmm.
If you join those lines, you will see that the gradient will basically follow some kind of pattern that will point to there. Okay, that's practical aspect of how you do that. Okay,
Okay. So
theoretical.
what yeah.
Hold on. Theoretically, what you do is you take a point. Okay,
Mm-hmm.
let's say the point P, and then you draw a like a tangential line. Okay, this is gonna be my E1 because that's my radial line, right?
Mm-hmm.
Then you connect another line, and that's gonna be my E2. You saw the arrows are pointed away from the positive charge and towards the negative charge, right?
Yeah.
So you have, I'm going to draw that in here, this part. So you have two vectors, E2 and E1. And that's where the electric fields are acting, right? These are the two electric fields because of charges Q1, for example, or Q2, right?
Mm-hmm.
And theoretically, you also know the distance R1 and R2.
Yep.
So E1 comes out because the formula is E equals to K Q over R square, right? So E1 will be K Q1 over R1 square. E2 will be K Q2 over R2 square, right?
Mm-hmm.
So you have those E1 and E2 values that is indicated on the right here, right? E1
Yep.
and E2. And once you have that, you then end up drawing completing the parallelogram or drawing the triangle to complete that, right? And there are different ways to, if you do it geometrically, it's that. Otherwise, what you end up doing is that you split this into X component and Y component, numerically, that is E1 and E2, E1 and E2 both split into its component, right? So this E1 has X component and the Y component. E2 has the X component and the Y component, right?
Yep.
Can you see that okay?
Yep.
So this vector over here is E1X, and that second vector over here, because of the projection of E2 over here, is E2x, and you add them together to get a new vector. That's going to be this vector. That is my EX. Okay.
Okay.
And then you can see this is already shadow of this vector. Do you see that?
Mm-hmm.
The X shadow, X component, right? And then on the other side, the Y component over here for this guy is here, right? So that y component would come out. So I'm gonna erase this thing a little bit here. So your y component for E1 is, this is my E1y. And then the other one, E2, has the y component. That's E2y. So when you put them together, one is up positive, another is down negative. So if you subtract both of them, right, this is like a 5 minus 2 kind of thing. So you get like a little bit here positive, right?
Yep.
And you can see that makes the y component of the vector E. So that's going to be my EY. Okay.
Okay.
So you end up with x component of the first, x component of the second, y component of the first, y component of the first here down, y component of the second, and then when this is plus, this is minus, this is plus, this is plus. So these two add together to give you a vector, that is Ex, and then these to subtract together to give you another vector, that is Ey, right? Now you have Ex and Ey, and if you complete a parallelogram, then you see that this is my vector E, that is Pythagorean, right?
Mhm.
Magnitude of the E is Ex square plus Ey square, and then take the square root. And what is that angle alpha? Angle alpha is given by SOHCAHTOA, tan inverse of Ey over Ex. So mathematically, how you do it, my friend, okay?
Mhm.
And practically, you have seen how to do that. Does that make sense?
Yeah. Everything making sense.
Okay, so you can do it practically as we did it in the lab, where we calculate the equipotential, right?
Hmm.
So, like this is what we did. We have equipotential surface, you draw the perpendicular to the equipotential surface, and you do that. Or you can do it practically, I mean, using math, by using two way. One is to just do the graphical way, where you have the x component and y component, or you can draw out a radial vector E1 and E2, and then you find the sum by you completing the triangle or the rectangle. Once you do that, your final value comes out as the application of the Pythagorean. So that's the basic vector math, my friend. I
Yeah,
hope
yeah, yeah.
some of it made sense, maybe.
Yeah, I just don't, because before I just don't understand how to draw the electric field. Like I know all the calculations, I know how to do those,
Mhm.
but now everything makes sense.
Thank
Thank
you.
you.
Yeah, thank you. Asking this helps also to see, what doesn't make sense. Yep. So the thing to notice is that in the case of force, you have two charges, there is the force between them. For electric field, if this is the charge Q, and you are finding the electric field or potential at point P, then all you're doing is you're drawing a line, finding the influence here, right?
Hmm.
Okay, let me not draw the arrow here because that can spook. So this place gets the effect, right?
Yeah,
E is at P, right? You're calculating E at this point due to the charge Q. So this is the distance R. It's like a standing near a oven, hot oven, and then how far you are, and then how much heat you feel. Does that make sense? If you are doing the
yeah,
barbecue, right? The heat that you receive is just inversely proportional to the distance, right?
yeah.
That's what you're doing.
It's
What is the electric field at that point because of the charge, and that distance is R square, right? Now,
mhm.
this is for only one, charge, but sometimes what happens is that you can have multiple charges. So there is one charge here, Q1, there is another charge here, Q2, there could be another charge here, Q3, right? And if you are here, point P, and you're trying to find the electric field, right? Then what you do, you connect the distance. That's a positive, so it's R1, right? So this is my E1. And then this is the distance that you're doing, right? This is E,
Mhm.
and this is the distance E3, right? So now you end up with E1 vector, E2 vector, and then E3 vector, right?
Yeah,
So now how do you sorry. How do you find the total? You can either do vector way, which is basically what you can do is you have E1, E2, and then E3, uh, something like that. E3, the total is gonna be this vector E, total E, right? As you
Yeah.
remember, the vector sum is basically joining the head and tail to each other to find the total, which is joined by adding the tail to, sorry, joining the tail to the head of the last. So if you do that, this is my net vector E, right? That's my vector. So, this can be done two ways, right? Again, this can be either done graphically like this, or you can take the table where you have the E theta, E cosine theta, and E sine theta. That's what we did whenever we were working on the
On the
problem,
yeah.
right? Over here,
Mhm.
we were calculating the E cosine theta and E sine theta. That's how you got the components, right? EX and EY. So this EX is E cosine theta, this EX is cosine theta, EY is E sine theta, and EY is E sine theta. So that's hopefully, now is connecting all the dots here. So for E1, you have the angle, you have the cosine theta and sine theta, it's going to be this and that. For E2, it's gonna be, the angle you're given or you can measure, and then AX is gonna be this, EY is gonna be that, and E3, for example, if you know the angle, EX is gonna be this, and EY is gonna be that. So you end up adding all the vectors, this, and that. You get the total vector. Over here, add all three to get a big vector. So this is my EX, this is my EY, and then we do the usual, which is you know, the Pythagorean.
That's okay. Yeah. The square root of the EX square plus the EY square.
Yep.
Then get the E in total.
Yeah.
Right?
That's all.
Okay. That's all.